Hello, welcome to my talk on thin airfoil theory. In this talk, the thin airfoil theory will be introduced, in which I will show how the problem is described and how the problem is solved. This theory was developed by Munk in 1922. This theory is based on the vortex principle and the Kutta condition, and it first theoretically shows the importance of the Kutta condition if lift is generated on the airfoil. This thin airfoil theory can be regarded as the first theory to prove the basic features of airfoils, such as the slope of the lift coefficient and the aerodynamic center. For simplifying the problem, in here we solve the problem for the symmetrical airfoils, and we will make some comparisons with the experimental data for different airfoils. These simple cases could be extended to more complicated cases. For instance, the cambered thin airfoils. An airfoil is a cross-section of a wing of an airplane, or of a blade of a rotor, or a propeller, or a turbine, and of a sail for a sailing boat. See the practical airfoils, different airfoils for different applications. Low-speed, ultralight machine. This airfoil for the airliners, this airfoil for the propeller blades, and this one for supersonic interceptors. And in here we can also find some natural airfoils like the blackbird, dragonfly, dolphin, etc. In studying the airfoil, we need to calculate the aerodynamic forces acting on the airfoil. So this including the lift air, which is perpendicular to the direction of the incoming flow. So this is the main topic in this talk. The drag D is parallel to the direction of the incoming flow. See here. And this lift and drag could form a resultant force R, showing here. And another important aspect for the airfoil is the aerodynamic center. For most practical airfoil, the aerodynamic center is at the quarter of the chord. We will consider this in this talk as well. And we also consider the aerodynamic force as the normal force, which is the force perpendicular to the chord of the airfoil, N here, and the actual force, A, which is parallel to the chord. So in this case, we can see this actual force could push the airfoil moving forward in the direction of the airfoil chord. And this is the force making the wind turbine to rotate to generate power. However, we must say the airfoil will not move forward in the direction of the airflow, because the air drag is always in the same direction of the airflow. See here. For studying the airfoil and all wings, we have many different methods. Some might be quite simple, while others might be very complicated. Currently, we have the method, the thin airfoil theory for inviscid flows. This theory will examine the lift and the moment. So this theory is valid for thin airfoil in the small angle of attack. So this is the topic for this talk. The more complicated method would be conformal transformation. It is the method working for inviscid flows, so the lift and the moment can be calculated. So this method can be varied for all airfoils in small angle of attack. So these two methods were developed in 1920s and 1930s when the computer was not available. So now we have the panel method for inviscid flow. Panel methods are based on potential flow theory, and in some cases, the viscous modification would be provided. So this is good for the pressure and flow field. We have 2D panel method for any airfoils in reasonable angle of attack, such as Xfoil, the open source of the panel method. And this panel method might include the air compressibility. 3D panel method, which can be used for whole aeroplane with the lifting and the long lifting bodies, and the air compressibility can be included in the analysis. The most complicated method would be the Navier-Stokes equation. So this is the method for solving the Navier-Stokes equation for the viscous flow. Thus, the lift, moment, drag, pressure, and the flow field would be calculated. This method should be valid for all structures, all angles of attack in theory, but may be questionable in the flow separations. Thin airfoil theory is a simple theory of airfoil in incompressible inviscid flows. It was developed by Max Munk in 1922 and further refined by Hermann Groet and others. In this thin airfoil theory, there are some essential assumptions. For instance, the aerodynamic forces, including the magnitude, direction, and the line of action, is only depend on the camber line, while the airfoil thickness is neglected. The ratio of maximum thickness to the chord is considered to be very small, and the theory is only working for the small angle of attack. Thus, the aerodynamic features would be all linear. A Kutta condition must be satisfied at the trailing edge of the thin airfoils. In all, this theory idealizes the flow around the airfoil. That is, the airfoil is represented by the camber line only. The thin airfoil theory was particularly important because it is theoretically prove some important properties of the airfoil. For instance, the theoretic left coefficient for thin airfoil would be given by this formula. Here, CL0 would be 0 for symmetrical airfoils. And it is proved the aerodynamic center lies at the quarter of the chord behind the leading edge. For studying the thin airfoil, vorticity is distributed on the camber line. See here. The vorticity strength is given by gamma S, and the circulation on the thin airfoil due to the vorticity is given by this gamma, and based on the Kutta-Yukovsky theorem, the lift of the airfoil would be calculated as this. It is well known to generate the relevant lift on the airfoil in the inviscid flow, Kutta condition must be satisfied. That is, the vorticity must be zero at the trailing edge, mathematically in a form as this. So generally, for the Kutta condition, we have two different trailing edge for the airfoil, the sharp angle of the trailing edge. In this case, V1 and V2 must be zero so that the flow at the trailing edge can be defined. And for the cusped trailing edge, we have velocity V1 and V2 from the upper surface and the lower surface. The Kutta condition would ask V1 equals V2. So in these two cases, the Kutta condition must be given by gamma c equaling to 0. So for the thin airfoil, this is the situation we need to consider. In this slide, we will calculate the induced velocity due to the vorticity distributed on the camber line. For instance, the vorticity in the segment ds will create a velocity dv at the point P. So the magnitude of the dv is calculated by this formula. Here r is the distance between the vorticity segment and the target point P. However, for the practical purpose, we are more interested in the normal velocity at the point P, which would be given by this. Here, theta 3 is the angle of the induced velocity and the normal direction. And the minus sign means the normal component of the induced velocity is in the opposite direction of the normal vector n. So consider the relation r given by this and ds given by this. So we can formulate the resultant vortex-induced normal velocity Vn as this. Now we are trying to solve the vorticity strength gamma. The first thing we need to build the equation for this vorticity. So now we consider the normal component of the free stream at the point P, which would be given by this. Here u0 is the velocity of the free stream, and alpha is the angle of attack here. And delta p is the angle between the tangent of the camber line and the horizontal line. And delta p in this figure is the negative gradient because the tangent of the camber line is below the horizontal line. Therefore, we put these two together, we have the normal component of the free stream given by this expression. And consider the normal component of the induced velocity. So, on the surface of the camber line, the total normal velocity on the camber line would be 0, given by this expression. Put all this together, we could have the mathematical equation as this. Here, we can see the mathematical equation is quite complicated. To solve this equation, two assumptions must be made here. The thin airfoil has a small camber. In the figure, the camber line is enlarged in the z direction for the purpose of an illustration. Therefore, we could have the small angles delta 1, delta 2, and delta 3, as well as the tangent at the camber line at the point P. So we have the approximations given by these expressions. And we also consider the angle of attack is small. Therefore, the expression can be approximated by this simple expression. As such, the mathematical equation can be simplified as this for the vorticity strength. Here, in this equation, in the integral of the expression, we can see there is a singularity on the left-hand side when z equals to x. This singularity may cause the problem in mathematics, but the integration itself has a limit value as shown by this equation. So the integration would have a value as this. If we imagine one approach to z equals to x from both sides, the denominator would have positive value in one direction, but a negative value in other direction. So the integration would cancel each other around the singularity. Even around the singularity, the integrand would be very large. Therefore, a limit value would be for the integration. We will see this later. And our next step is on how to solve this equation. For simplifying the solution, we first examine a simple case, the symmetric thin airfoil, which means the camber line of the airfoil would be on x-axis. See the plot here. Hence, the gradient of the camber line with regard to x would be 0, given by this. So the mathematical equation for the vorticity strength can be simplified as this. However, if the equation is in this form, it is still very difficult to solve. Munk in 1922 found a way to solve the equation by introducing a coordinate transform given by this kz. And this coordinate transform would lead the limit for the leading edge kz equaling to 0 would lead theta equaling 0. And at the trailing edge, kz equaling to c would lead to theta equaling to pi. And we have the expression for d kz expressed as this. Kutta condition now is expressed as gamma pi equaling to 0. For the specific point P on the thin airfoil, where kz equaling to x, which would correspond to a specific angle theta 0, given by the expression as this. So we can have x minus kz expressed as this. So after the coordinate transformation, the mathematical equation becomes as this, and the corresponding Kutta condition given by this. So following the reference, a solution to the vorticity strength can be given in this form. This should be obtained first by Munk in 1922. If we substitute this vortex strength into the left-hand side of this equation, we can see the value on the left-hand side would be given as this, and we separate the integration into two terms. We have this. Now we consider the integration identity. If you like to see, you can find the derivation for this integration identity from the reference here. So if we take n equaling to 0, we have the integration by this, and n equals 1, we have this. Obviously, this integration is the same as this, so it would be 0. And this integration would be same as this, so it equals to pi. Therefore, the value of the left-hand side would be this. So this is exactly the same as this. Therefore, we can confirm the vorticity strength in such a form is correct. Now here, we will have a look at the Kutta condition. So if we apply the Kutta condition at the chilling edge, when theta equals to pi, and we can calculate the vorticity gamma given by this, and we will have an undefined expression, meaning 0 divided by 0. This difficulty can be solved if we use the L'Hopital's rule following the reference given by this. The limit of both functions f(x) and gx, both are 0 in the limit, can be replaced by the limit of their differentiations given by this. As such, we apply this L'Hopital's rule into this vorticity at the chilling edge. We have the expression this and this. So this will lead to an expression as this. Thus, we can see the limit of the vortex at the chilling edge is 0. In here, I will show another approach to obtain the limit of the vorticity strength at the chilling edge, which is directly based on the trigonometric relations as this, and we will have the expression as this. Here we can cancel out the part of cosine theta divided by 2. So we have the expression as this, and we can see when theta approaches to pi, this expression would be 0. Therefore, the expression of the vorticity strength satisfies the Kutta condition. Once we have the vorticity distribution, we can calculate the circulation on the thin airfoil, capital gamma, given by this equation. And we can substitute the vorticity expression into this integral, and we can have the result at this. And then we can calculate the lift on the thin airfoil based on the Kutta-Joukowski theorem given by this. So we have the lift. This is the lift per unit span. If we plot the lift, it would be something like this. Here, we must note the lift is perpendicular to the incoming flow, not to the chord of the airfoil. And the lift coefficient would be given as this. And the result is in a very simple form, 2 pi times alpha. Here, alpha is the angle of attack in radians. In this slide, the aerodynamic moment on the thin airfoil with regard to the leading edge would be calculated given as this. Here, m0 means the moment with regard to the leading edge x equaling to 0. And the negative sign means the moment is lowered down, which is in the opposite direction with y-axis. In this plot, it is pointing into the screen. Using the following relation and the vortex expression, we could calculate m0, and we have the expression as this. So this will lead to a result as this. Here, again, the trigonometric relation given as this is used. Now we can calculate the pressure center xCp using this equation. The moment equals the lift times the pressure center, xcp. Here, negative sign means nose down. So if we use the value for m0 and L, we can obtain the pressure center xcp would be a quarter of the chord after the leading edge. And the moment coefficient would be given as this, and we can see this would be minus quarter of the lift coefficient. Generally, for most practical airfoil, the aerodynamic center is at x equals quarter of the chord. Since at the aerodynamic center, the moment coefficient would be a constant. Here is 0. If we check this moment with regard to the quarter chord, this moment would be 0. If you are interested in the calculation, you can do this yourself. In this slide, the comparisons are made for different airfoils. The first comparison is for the NACA 0009 and NACA 0015. Both are the normal NACA 4-digit symmetric airfoils. They have very similar features in geometry. The main difference between them is the thickness, 9% compared to 15%. Generally, NACA 0009 can be considered as the thin airfoil, but the NACA 0015 is a relatively thick airfoil, since the most useful airfoil would have a thickness of 12%. So the prediction uses the thin airfoil theory and the experimental data for these two airfoils. We can see in the small angles of attack, say less than 10 degrees, both airfoils have very close lift coefficient as the theoretical lift coefficient. And the large difference between these two airfoils is the lift coefficient in the stall condition here and here. And we can see from the comparison, NACA 0015 has a mild stall lift drop. The second comparison is for the NACA 0012 and the NACA 0012-64. Both symmetric airfoils have same thickness, but the latter is the modified version of the former one, with the main difference of the maximum thickness occurs at 40% of the chord, the former at 30%. See the profile comparison. If we look at the experimental data and the prediction from the thin airfoil theory, we can see, again for the lift coefficient, in the small angle of attack, both symmetric airfoils are very similar, and the slope of the lift coefficient are both very close to that from the thin airfoil theory. And from the comparison, we can see both airfoils have very similar stall characteristics, see here and here. In this slide, the moment coefficients are compared for different airfoils. In the small angle of attack, both NACA 0009 and NACA 0012 would have very small moment coefficient regarding to the quarter chord. Again, from this comparison, the large deviation occurs at the large angle of attack, where the stall happens. Similarly, for the NACA 0012 and NACA 0012-64, when the angle of attack is small, The moment coefficient from the thin airfoil theory is very close to the experiment data, but when the angle is more than 12 degrees, the large deviation would happen from the thin airfoil theory. See here.